Cannot hear me. Okay, online live people, you should be able to hear me now. My mic was on mute. Online live people, can you hear me? We'll hear from them soon. I'm about to start going through notation. There we go. Let's start going through notation here. Notation start, and let's see what you guys know. Okay. And there I am. So with the notation, let's go over some very, very important notation, and let's start this up. Let's insert here, and what notation can you guys tell me? Online, start giving off that notation. It's important that you can tell me it, and we'll put some stuff here in a moment. But let's go through some of the easiest stuff. Like, what is P? Like, what is P? True proportion. I might misspell stuff. We'll find out when I get that little red bar in Word. But P is the true proportion. Does that make sense? The reason we need to know all this is because it's in the formula. Hey, HD and Kajal and Ashley. Hey, guys. Awesome to have you here. Feel free to ask those questions. Sorry if the video of me is a little jittery with what they're seeing online, but focus in on the Word document, and I think the audio is pretty good. We've got my good microphone here, and there's a bit of a delay, and when we do this online later, that's why we won't use my little tiny MacBook Air and a Wi-Fi connection to start doing this. So we've got P, which is the true proportion. Let's kind of go off of P right here and think of something very close to P. And how about we do P? We could do P hat. How about P with a little subscript on it? P naught. Now, anytime we add naught to this, anytime we add naught, what is it every time we add naught? Every time we add naught, it's what? Hypothesized. It's so fun not being able to see it for a moment. I got to type blindly, so they see it later. P naught. And I just want to review here because when you see that naught on something, you should think hypothesized. So although we're not going to write it down right now, what if you saw mu naught? Hypothesized mean. What if you saw maybe beta naught? Now that won't be on this test. Do what? Or sigma naught. Sigma naught would be the hypothesized standard deviation. Now, don't worry about those. We're not going to have sigma naught. We're not going to have beta naught. Beta naught would be the hypothesized coefficient for a regression model. We're not going to do those on this test. We're only going to focus in on P naught and mu naught. But what do we notice about naught every time it's in a notation? It means what? Hypothesized. And it'll always go with the null. Things like P equals P naught. You won't write P equals P naught. You'll put in the value for P naught that you have. Like when a question asks you, do you think 50% of students want a Taco Bell on campus? So what is 50%? It's what you're testing. It's the hypothesized amount. We might do a test to see if the true proportion of students who want a Taco Bell on campus is equal to 50%, or the true proportion of students who want a Taco Bell on campus, if we're thinking about building it, might be what to 50%? Greater than. Does that make sense? If we're looking for evidence to build a Taco Bell, which we definitely should, we might have P equals P naught as the null, and P greater than P naught as the alternative. And what did we hypothesize as the true proportion right now? 50% in this Taco Bell example. Some early morning Taco Bell examples. So anytime you see naught, what should you think? Hypothesized. P, proportion. Naught, hypothesized proportion. So Mohammed, you mentioned one just a second ago. Let's go ahead and throw in, we got to go to our equation editor now. There we are back on this screen. Oh no, please don't give me spinning wheel of death. Ooh, that scared me. I'm still getting scared. So let's go right here. Let's go to equation editor. Online people, how is the stream quality and can you hear everything properly, online people? I'm trying not to turn away so much when I talk because I want you guys to be able to hear. And let's go right here to a little hat symbol and we'll move this here and let's bring it all the way. When I put in P hat, what is P hat going to be? What is P hat? P hat is what? Sample proportion. So P hat is the sample proportion. Okay, Okay, good. It seems like it's all right stream quality. I hope it's all right there. Thank you, Chelsea. So P hat is sample proportion. If you notice, I'm kind of going through and doing all the proportion stuff right here, so you can try to just get it down. What do you notice about all the proportion notation? Well, what does it start with? It all starts with P. And this is kind of key because when you do questions, you should circle the numbers in the questions. Every time you come to a question, if you see like, we went out and talked to 100 UT students, and this is probably one of the best global ones, we went out and talked to 100 UT students, you would have what? Exactly. So the sample size is N. Nice job, answers online also. And it changed it to a capital N. We're not going to let it do that. Capital N is actually population size. Nice job. So it's lowercase n. Sometimes formulas mess around with that. Lowercase n is sample size. Pretty easy one there, but it's one we should always remember. And when you read a problem and it says, we went out and talked to 100 students, go in there and circle that 100 and write next to it n. You might see something like, and let's put this next to it also, out of those 100 students, 62 of them wanted a Taco Bell. Well, I already gave away the answer. This is something people often forget with this one, that 62, and this is number of successes in sample. X can be different things. X can just be a variable. But as you work through each question, circle the numbers. And you won't usually see, I don't know, during the test. You're like, wait a minute. Brian said that we went out and spoke to 100 students, and 62 of them want a Taco Bell on campus. What is the sample proportion? And the sample proportion would be 0.62. Correct right there, Mohammed. Exactly. So, Mubarak, I want to try something. Online people, Mubarak, just say hi. Hi. So if you heard him say hi, I want you to tell me online yes or no. I've got my mic in a dipolar or bipolar direction, and so if you can hear that, and I hope the stream quality looks very fuzzy online. I might even zoom in a little bit here. There we go. Maybe that'll help. Obviously, streaming from G2 is not the best idea. Wow, I hope it's decent stream quality. Onliners, tell me what's happening at all times, because I hope this is going all right. Fingers crossed. If not, it will be recorded and up later, so we might have to just let the stream build online. So we are going through notation right now. We have everything on here. Next, let's hop. Well, I tell you guys what. Awesome. Words are clear, and you guys can see what I'm writing. So with this online right now, do you guys want to do a practice problem with this notation, or would you like to continue notation? You guys tell me. It's like a choose your own adventure right now. Who wants practice problem with the notation? Who wants to continue notation? Okay, let's continue this notation. And next, we're going to make another subgroup here, and we're going to go straight to y bar. Let's do mu, because we'll kind of keep them in order. Let's go here to insert. We got to go to insert. It's actually easiest to get to mu on a Mac if you go to equation. Look at that lag. And where's my mu at? I said it was easy. And do you guys see mu? I thought it was here. Oh, it's one screen over. And there's mu. So there is mu. And let's go right here. We will do a practice problem soon. You are outvoted, Chelsea. And what is mu? What is mu? It is the true mean. And whenever we say true mean, that means, or true proportion, that is the true for the population. That is like the GPA of all UT students, or the height of all UT students, or the weight of all UT students, or the average number of siblings that UT students have. And I should say, the true average weight of UT students, because we're not talking about one here, we're talking about an average for all. And what do you notice about all of these questions I'm asking for mu? Quantitative. All of these values means are quantitative. Always go back to the question like, what is your weight? What is your height? How many siblings do you have? How much is your income? How many miles do you live from UT? How many miles did you run last week? These are all quantitative questions. To contrast that with the last block of questions that I have, maybe we'll try to make it more clear. Let's put right here, and let's put a little thing right here. Categorical questions. These are all related to categorical questions. Things like, Do you want a Taco Bell on campus? What is your gender? What state were you born in? What's another categorical question? You guys throw me a few right here. Make sure you get it. Remember when we did this in class, everyone went around and said a few? What else are other categorical questions while I edit a little more of this document? It looks like they did not hear you, Mubarak. What are other categorical questions?
Are you born in Tennessee?
Are you born in Tennessee?
Yes or no question.
Yes. Everything yes or no questions are categorical questions, and that would lead to proportions. So whenever you see something like on the practice test, which we may take a look at in a little bit here, the practice test has things like, we went out and talked to UT sophomores and wanted to see if they recycle. So we'd ask somebody, do you recycle? Now be careful, and here's where people get confused. The question has in it numbers, like, 150 of the UT sophomores, I think we spoke to like 150 and 82 of them recycled. So people are like, wait, Brian, that's a quantitative number right there. That's a real number. And that's what quantitative data is. But always go to the question asked. So when the test question says, we ask students, do they recycle? No student walks up to you and gives you an answer, 82. If you ask someone, do you recycle, what do you say, Yusuf?
Yes.
You say, yes. Oh, Yusuf recycles. That's awesome. So they say yes or no. So be careful. Don't be tricked. Now, the 82 in that question, where I said 82 students recycled, just to practice a review right here, that 82 would be what? You would circle it and right next to it what? 82, you've got a notation cheat sheet right here. It would right next to it, X. You'd write next to that 82X. And I also gave another number, what? Sample size of 150, circle 150, because 82 out of 150 students recycle. 82 is X, 150 is N, X over N equals P hat. And you can see the notation in the background right here. Yes, it does say quantitative questions. I'm so sorry. I hope it does say quantitative questions. I think the stream quality will be better once this is recorded. If I'm seeing what you're seeing, and that's why I zoomed in, it is very hard to read what I'm writing. I'm so sorry. It's streaming from down under in the here, and I hope once this is recorded. So if you come into the stream, Chelsea and everyone else, if people come onto the stream, they're like, this video quality is horrible. Brian, what are you doing? Tell them after this is recorded, I think the stream quality will be better. Okay, words are still clear for you, yes. So if anyone comes on complaining, you're like, this is horrible, Brian, what are you doing? Just say, it'll be better once it's recorded, and you guys can use this over the weekend, which is why I wanted to do it now, so you have this opportunity to watch back and review this. And I'm trying to make it as big and clear as possible for them to see, and that's what they see online right now, and they also see me. Okay, let's watch it be blurry in the recording, but it shouldn't be, because Chelsea can see it clearly. So let's continue on. We've got mu, and from mu, we're going to write the one right below it that's like mu. And what are we going to write that's just like mu? Mu naught. And we reviewed this earlier. You should know by now that anytime we put a naught, we just change what this is called. Oh my, it went away. So anytime we have a naught here, we just change it. Instead of being the true mean, it's going to be the what? Hypothesized mean. So it's going to be the hypothesized mean. There we go. I don't know how to copy paste. And let's go up here. So this is going to be the hypothesized mean now. And I want you to think about, this is where you can really help yourself out. If you think, how in a question would this be worded? So practice and think about how we could surprise you in a question with mu naught. Let's say we say, you are doing an experiment on a local pond. You want to see if the contaminants in the pond are greater than 1.2 parts per million. So what is 1.2? The hypothesized mean. Does that make sense? So you would take samples of water and see if in your samples the average contaminants is greater than 1.2 parts per million. So this would help you write the null and the alternative. Yes, thank you. Tell them to turn up those settings. So you would see if the contaminants are greater than 1.2 parts per million. So this is where we would have things like the null, and let's write this in right here on the side. We're just going to add little notes here. We're going to write HO, and we're going to put a little null hypothesis right here. And this is going to be confusing, but listen carefully, because when we write the null, we say that the what? The true mean The null states that the true mean is what? Equal to the hypothesized mean. So, dry throat. So the null says the true mean is equal to the hypothesized mean. And in my example, I stated that the hypothesized mean was what? Say it again. Well, remember, the hypothesized mean will just be a number. So 1.2. In my example, I said you want to see if the local pond has a contaminants that is greater than 1.2 parts per million. And although I said greater than, why did I write equals? Because you can say this, and we'll do this a lot throughout today, the null always has the equal sign. Does that make sense? Every time you write a null, the null always has the equal sign. And one of the great things, this is just kind of a review within the notation review. When you add this in right here, let's just do a little bit of notation. And you probably want to write 1.2 parts per million. So that would be parts per million right there. So the null would be that the true contaminants of this lake is equal to 1.2 parts per million. And if you wanted to write the alternative for this question, which we'll just write very briefly, all you have to do to write the alternative, and this is the way to practice, do not change anything other than, well, you want to change this to an A. Do not change, I think, Muhammad, you got it. What else do we change? Change only the sign. A lot of people make a mistake here. They start changing the mu to a y bar, and we'll mention that next. They start changing the numbers, and they use the sample mean. No. The only change between writing your null and alternative is that sign. And when I go through this especially, we talk about what is in position 1 right here stays the same. If you notice what I'm hovering over right now is position 1. And whatever is in position 1 stays exactly the same. What other position in this stays exactly the same? What is ever in position 3, right? The last position. So whatever value we are testing stays exactly the same. And the null always has the what? The equal sign. So you've got a lot of structure here you can work with. These would be questions where we ask you to write the notation. So whenever you see write the null and alternative in statistical notation, we're asking for something like this. We didn't do it with the proportion a moment ago. We'll do some questions throughout today where we practice writing the null and alternative with proportions in statistical notation. But right here, you can see how to write the null and alternative in statistical notation using the mean. And if you notice, this value right here is what? We'll rewind time just so you can see, go back in time. That value right there is hypothesized value, according to the null, the hypothesized value. And in a question, I'll say a different one right here. You are wondering what the average score on the Stat 201 first test actually is. You believe that it is lower than an 80. You go out and talk to 100 students and find that their average was 72 with a mean of 5, with a standard deviation of 5. I said a lot right there. It's a lot to catch.
72.
No, oh no, 72. We'll write that right here. If you heard, and you could rewind the video if you're watching live, 72 was the what? As long as I remember all those numbers, I think I can repeat it. 72 was actually, 72 was actually, I think, does that look like a bar? No, double over bar. I'm looking for a bar, and I usually know where it's at. There's the bar. 72 was the what? Y bar is the sure, we'll keep it like that. 72 is the sample mean. Because I said you went out and found that there was an average of a 72. Does that make sense? What we found was there was an average of a 72. So 72 would be the sample mean. I can't escape the equation editor. So 72 is the sample mean. What else did I tell you? You want to see if the average is what? You want to see if it's lower than 80. And so the null would be, so try this right now. If you're practicing online or in person, try writing the null and alternative right now. So try writing the null and alternative, because we just stated, and I'll restate the problem again, so practice this up on your sheet of paper. You want to see if the average on the Stat 201 test is lower than an 80. You want to see if the average on the Stat 201 test is lower than an 80. So you should have written what? The null what? I'll write it right here. These are all practice problems, writing nulls and alternatives. So what would be your null? The null states that the true mean is what? Is equal to 80. The alternative states, and we'll write that right down here. The alternative states that the true mean is less than 80. And you notice the only things I'm changing right here is just changing this to less than, and everything stays the same. So I'll repeat the question again, and you can see the notation up there. The question was, you want to find out what the true score on the Stat 201 exam is. You believe it's lower than an 80. So when you go out and speak to 100 students and find an average of a 72 with a standard deviation of 5. Now if you notice, where did that average of 72 come from? It came from your sample. That makes it the sample mean. Does that make sense? So be careful, there's a lot of means. You might hear a value being tested, but the value being tested doesn't come from any data. The hypothesized value of 80 could be anything. I could just change that randomly. It's not data dependent. Also, you have to look at the question to figure out the what for the alternative. Whenever we write an alternative, how do we figure out the sign of it? We look at the question. So when I say something like, we want to see if the average is less than 80, that tells you the direction of the alternative. Now the question could say something like, we want to see if the average is 80. If the question just said, we want to see if the average is 80, what would be the sign of the alternative? It would be does not equals. Does that make sense? If there is no way, if the question does not go a certain way, if it doesn't say, let's see if it's greater than, less than, more, decreased, increased, it could say different, it could say changed. But if it doesn't give anything, it's a does not equals. And the words I just said a moment ago, like changed or different, those would also be does not equals. There's some really great My Pearson questions that kind of try to trick you in a good way. It's one of my favorite ones, and my gosh, people in Stat Lab hate it. But now we're asking, you just want to see if it's 80. So I changed the question now to where it would read, you want to see if the average on the exam was 80. Where there's no, you want to see less than anything, you just want to see if it is 80. So the alternative if it is 80 is not 80. So one of my favorite questions on My Pearson is the one that asks you about the attendance. You guys remember that attendance one? And then it says they saw that it dropped. And then it says officials would note any change, or officials want to see if there's any change. So of course numbers go up and down, right? If you go out and collect data, I'm going to see something above or below. So the question might say we saw a mean that was below 80 in our sample. We want to see if the exam is different than 80 or has changed. Always be very careful. We try to make it more clear on the test. We're not going to try to trick you like My Pearson, but I do kind of like that question because although the mean is lower, we don't want to just go with, or in that question's proportion actually, we don't just go with let's test less than because we saw something less than the hypothesized value. Look to the question and the wording of the question to get the sign. Only a few other things here. What else do we have with quantitative values? Try to go through your mind right now and tell me a value for quantitative values that we also could look at. S, exactly what I was thinking. Hopefully, it's doing capital S. And S equals what? Yep, and I'm going to write sample standard deviation. Sample standard deviation is S. And let's add in one more thing here also. What else do you think I'm going to add in now right after S with sample standard deviation?
Sample size?
Well, we have sample size up. We have sample size as like a global thing. We just did S. So now I'm going to do sigma. Nice job. So we're going to do sigma right here. Sigma is what? True standard. So whenever I say true, true is for a population. True and population are synonymous. So true and population are synonymous. Does that make sense? When I say true standard deviation, that's for all students here at UT. When I say true mean, that is for all students at UT. When I say hypothesize, that's just a number I'm making up. It's just given in the question. It's something you want to test. So there's just some small wording. Sample is what you get from a sample size. So sample standard deviation has to have within an n. Also sample mean has to have an n. Also sample proportion has to have an n. Does that all make sense? Whenever you say sample, you should be looking at a sample size it came from. So make sure you know this notation. I also want to point out something big here too. What do you notice about everything that is true? Pretty much all of them are Greek letters. So when you see these Greek letters or these capital letters like capital P, we see here that the capital P is the true proportion. So I usually say the Greek population or the big ones are the populations. We're the small sample statistics. Small sample statistics, you don't see Greek letters for sample statistics. You see S, you see N, and not capital N, just little n. So all these things right here, seeing what the messages are online, and sorry online, I hope there's not too much of a lag. You are about 15 seconds back in time. This is why when we do the new online class, we will not be streaming from my little MacBook, and we will not be doing it on Wi-Fi. This is what we've been testing out lately, and it's shown us what power we need, and that's why we got that new computer. So let's think, are there any other, you know what we should do right now? Let's hop over here, and let's just take a quick peek at the formula sheet. Oh, that's the topics. Topics, not so much. Oh, the internet's not going to have fun with me right now. Let's pray. This is when you are streaming and doing all this. Okay, we want to go to the formula sheet. Chelsea and everyone, can you still see the screen clearly, and can you still hear me clearly, onliners? Can you still hear and see me clearly? Well, not me so much. I probably look blurry. We'll see what the onliners say. We have 7 people watching. That's good for right now. You ever click on something, it just takes an hour to load? 19 pages. A lot of people ask me, Brian, will the practice test look a lot like our test? And the answer is yes. Every year we have a lot of the same people writing the test. We can't promise you that it's going to look just like the test. It's not the way we write tests. We don't just write the same test every year. But we're the same people. We're going to come up with similar questions every year. It's not going to change drastically, but if you just study the practice test, you probably won't ace this test. You need to understand how the practice test questions work. So let's see, I see a bunch of Y bars. Wait, down here I see a 1 on this. Let's zoom in really good so they can see this online. So wait, if this has 1 on it, Brian didn't cover what Y bar 1 is. What is Y bar 1 and what's going on with Y bar 1? What does that mean? That's the sample mean for group 1. Such as a question could ask you, I think one of the ones on the practice test says, let's look at the heights of men from USA and from Britain. So Y bar 1 might be the mean height of men from USA. And Y bar 2 would be the sample mean of heights from men from Britain. What would S1 be? The standard deviation for the first group. S2, standard deviation for the second group. N1, sample size for first group. N2, sample size for second group. I'm trying to see if there's anything else we've missed. We didn't talk about the t-statistic. That might be better mentioned at a separate time. Let's zoom out here a little bit. I'll zoom in nice and big so the onliners can see. We have p hat. Oh, q hat. Let's do q hat. We should put that on here. What is, ooh, my, this is just scary when I see that. So what, anytime we have q, and I'm just going to write q hat. So, or we could, anytime we have a q, what is q when it comes to, I guess let's put it, sure. Oh, we'll do q naught. So what would q naught be? It's the complement of the true proportion. So where's my subscript? Q naught is the complement. And you could do q hat. Okay, we'll try to make it bigger for the onliners. They say the practice test is pretty small. So I'm going to have to zoom in really well for that. So complement with an E of true proportion. So Q naught is the complement. Oops. Everyone correct me. What did I do wrong here? Should be hypothesized. And do what? Yeah, I guess. It could be small. Let's do that. So it can be small. Don't worry about that too much. I do agree. And now we went a little bit big on the text there. Let's decrease that one. So Q naught is the complement of the hypothesized proportion. Q is the complement of the true proportion. Q hat is the complement of the sample proportion. Okay, awesome. Well then, hopefully the video renders well, and maybe we just have an audiobook. Ooh. Sorry, onliners. Video down below here is not that great. Funny, my apartment has better video than this room on campus, because I've been able to stream the Kahoots. So if I were to stream the Kahoot from this room, you should watch this online video. It is not doing well. I hope you guys can watch this later. So Q, complement of true proportion. Q naught, complement, hypothesized proportion. Q hat, complement, what proportion? Q hat, complement, sample proportion. What is the complement? You guys ready to play the complement game? It's not where you say nice things to me. So the complement game works the following way. If P is 0.2, Q is 0.8. If P is 0.6, Q is 0.4. If P is 0.1, Q is 0.9. Do you guys get how to play it? Pretty quick and easy when we look at what's on these formulas. If you ever have to find a complement, and you see we do have here Q naught, so I'm trying to make this really nice and big for the onliners to see. I guess that's as big as I can make it, onliners. But Q naught right there is the complement of the hypothesized proportion. Q naught, on that formula I'm hovering over, is the complement of the hypothesized proportion. So if Brian said in a test question, I did one earlier, we want to see if 50% of students want a Taco Bell on campus. UT will build one if more than 50% wants a Taco Bell. And with that, we'd have P naught equals to 0.5, and interestingly enough, Q naught would equal 0.5. It's just the complement, whatever adds up to 100%. So let's take a look right here. I don't know if we missed anything else. Z and T are test statistics, or they're critical values. Do you guys see anything else in the formulas? We have down here observed and expected. I guess you guys want to add those in? Let's put this in for chi-squared. We're going to hop from this, and we're going to start doing some test questions here right after we do all the notation. I want you guys to look at that formula sheet and be able to look at a test question and be able to understand what the test question is telling you. So with this right here, let's go to chi-squared stuff. So we are on the screen. And let's go to squared. Chi-squared. So when it comes to the chi-squared, do a page break, we're good. So the chi-squared has a few things. One, it has in it the observed values. And we're going to call these counts also. The actual amount, or we should say number reported. So whenever we look at a contingency table will have in it the counts. I mean, it must. It doesn't must have to have them, but most contingency tables will show you the counts. It's like when we say there are 5 men in this room, and 1, 2, oh, there's more than 5. 7 men in this room, and 1 man is wearing a hat. So we can do counts, right? Now, if you notice, chi-squared takes what kind of data? Chi-squared takes what kind of data? Chi-squared takes count data, or categorical data, which is one of your conditions. So we're kind of merging topics here by saying, what are the observed? So you would merely have 2 categorical questions. What is your gender? Are you wearing a hat? And both of those must be answered with a yes, no, or any sort of kind of category answer. Does that make sense? This is what we are doing with the chi-squared. The chi-squared will give us count data. Never stream from G2 again. I have noted this. They are very back in time on minors. And so let's make it a tiny bit. There we go. So we have the observed, which are the counts. And then next we have with chi-squared, what do we have next? We also have the expected. So it's important to know what your expecteds are. And what the expecteds are actually what we would expect via random chance. So the expected values are merely going to be row total times column total. I guess let's do a definition instead. Row total times column total over grand total. Well, what does that mean? Let's talk about it briefly here. Row total times column total over grand total, and we will be doing examples later, but this would be the values expected with the null. So that might be a little more in depth than we get into, but what do we mean by the expecteds? It's kind of like if the two variables are what of each other. Think chi-squareds, think your null and alternative. If the two variables are independent, because this is the chi-squared test of independence. Does that make sense? If the two variables are independent, what would we expect? And let's do a very quick example, which I think you'll get. I have 200 students in my class. 100 of those students are athletes. 100 of the students in my class pass. How many athletes would you expect to pass by random chance? Now remember, I have 200 students, 100 are athletes, and 100 students pass. So 100 students are not athletes, right? And 100 students don't pass. So how many athletes would you expect by random chance to pass? Well, just think. Half my students are athletes, half my students pass. How many athletes would you expect to pass? Give me an exact number. 50. Did everyone hear that? Because what percent of students pass? Half my students. How many athletes are there? 100 athletes. So wouldn't you expect, just without knowing anything, that 50 athletes would pass? And you can actually do this if you want. The equation would be 100 times 100 over 200. Just double check it on your calculator real quick. That should be 50. 100 times 100 over 200 should be 50. And you've just done row total times column total over grand total. It's 50. And it makes sense, right? If half my students are athletes and half my students pass, with just knowing that, well, if there is nothing going on here and it's just by random chance, I'd expect 50 athletes to pass because I'd expect half the athletes to pass. And that's what this is expected is doing. We have one last thing right here. Let's put in a chi-squared. I'm going to do a big X instead of a chi. Should we look it up? Should we look up the chi? Let's see if it's nice here in the notation early. Let's go to insert and see if it has all of our statistical notation. The advanced browser on a PC is actually way better for some reason. It's like one of the few things I like better on a PC. And do you guys see the chi? Oh, wait, is that it? What is that? Those are not chi. We should see it. That's not chi. It should look like an X. Is there, oh, I bet that's chi. There's chi. A lot of people say chi. Is anyone in like chi omega or anything, or sigma chi? It's definitely not chi. So not chi. That is chi, and we're going to make it a chi-squared. So chi-squared is going to be our test statistic. You know your computer's having a hard time when you click buttons in Word and it takes a while to load. So that is not a good sign. I'm just hoping we don't like just suddenly crash. So the chi-squared, we'll add in a few other things. We're almost done with notation. Then we're going to let you guys pick my next topic. Thank you guys so much for being here live. Chi-squared is the test statistic right here. So the chi-squared is a test statistic, and it's found via the formulas. We'll be able to see it better live later. We get all of the cell chi-squareds right here. Does everyone see where it says cell, or I wish it said cell, I don't know why it doesn't. But the chi-squared test statistic is the sum of all the cell chi-squareds. Technically, this, what you see right here, this observed minus expected squared over expected, that right there, that formula is the formula for a cell chi-squared. And what did I just review previously? I first started out by reviewing what? The observed. That's the actual amount that you get, sometimes called the count, or just what we get when we say there are 5 individuals who have this quality and this quality. And then the expected must be found via the formula what? row total times column total over grand total. So you have to solve for the expecteds. And then from the expecteds, we get the what? Each individual cell chi-squared. Then how do we get the chi-squared test statistic? Add up all the cell chi-squareds. You notice it says sum of all the observed minus expected squared over expecteds. And those are all the cell chi-squareds. And then this is called the Pearson in your jump output. Remember, you go to my Pearson, do your assignments, and we always say in my class, the Pearson has your p-value. The Pearson has your p-value. So when you see that down low in the output, the Pearson has your p-value. We'll be looking at lots of output today. So let's hop back here. We've got the chi-squared test statistic. I guess we'll add in one or two more things right here. We've got here the t, and the t is also a what? Test statistic. And then up here we have in a what? A z, and the z is also a test statistic. And then we also have in, not for this one, the t distribution has with it. Can we get this all on one page? Yes, we can. So we also have with the t must have with it, every t will always have what? These are things you should know pretty quickly. Every t, we know which t it is by its degrees of freedom. Degrees of freedom tells us which t we are using, but then also, there's my page break going haywire, also, we have what else? The chi-squared will also have with it degrees of freedom. And we're going to do one last thing here on this notation review. We're just going to go over our degrees of freedom review. So this is our last bit, I think, for notation that we're going to head off to your guys' topic. These are, let's double check the formula sheet because I think I've mentioned everything on the formula sheet now, which I don't think I've done a video on this yet, and I don't think it's in my main review where I've really gone in depth on the formula sheet. You notice the formula sheet does give you the formulas for the degrees of freedom. You've got the 3 different formulas right here, and I'll mention them that way then. So, and we'll see if we missed anything. When you have a 1 sample t, when you have a 1 sample t, and what does a 1 sample t mean? A 1 sample t would be the following. We went out and talked to UT students. Another example would be a 1 sample t would be, I went to Walmart to ask people what they think of the sale prices, like what they paid on their, like what was the average price of a Walmart visit. So we went and asked people how much did they pay, and we found the average price from that sample. Now, a 2 sample t would be, I went to Walmart and I went to a campus store at UT to compare how much people are spending. So maybe we went to students when they come to campus, we want to see if the average ticket price or the average sale at Walmart is higher than the sale at UT. Now we're going to compare 2 means. Does everyone hear kind of the difference between 2 means and 1 means? You could also do one proportion, like the proportion of people at Walmart who buy milk. So you might say, I went to Walmart to find the proportion of people who buy milk. So what would you ask someone leaving Walmart? It'd be a little bit weird. You'd simply walk up to them and say, did you? Just walk up to an individual and say, did you buy milk? So if we want to find the true proportion of people at Walmart who buy milk, we'd go up and ask them that categorical question. Would that be 1 sample or 2? It'd be 1 sample or 2. I'm just at Walmart. So the 1 sample or 2 is based on how many groups do you get. Does that make sense? When we do a 1 sample t, which you see on here where it says 1 sample, 1 sample. So those are just where you go to one spot and get one group of data. But if you want to see if more people, you guys remember back in the day when we had a Walmart and a Publix? It's like forever ago now. That joke's not going to age well. But if you were to go to the Walmart and Publix, and if you wanted to see if more people are buying milk at Publix than at Walmart, now we didn't do this on our test, would that be think of this, would that be 1 sample mean, 2 sample mean, 1 sample proportion, or 2 sample proportion? You go to Walmart and Publix and try to figure out the differences between the proportion of people who are buying milk, and I basically gave it away. It'd be how many samples? 2 samples, proportions. Now that's not on this test, But if you can identify that, you can hear the difference between means and proportions and 1 and 2 sample. Does that make sense? You can switch the question. You want to see if people spend more at Publix than they do at Walmart. Now we're asking people, how much did you spend? And how much did you spend is a what question? Quantitative, and Walmart and Publix means there's how many samples? 2 samples. Now let's review degrees of freedom and then hop to our next topic. Right on time to meet our 10 a.m. guideline. So right here, if we are doing degrees of freedom for a 1 sample T, which would be like we went to Walmart and asked them how much on average do they spend, we would be using the formula, which I have on the screen, n minus 1. Sample size minus 1. So it's pretty easy to remember and put in your head, but it is on the formula sheet. But for a 1 sample T, remember T's always have degrees of freedom, the formula is n minus 1. I spoke to 92 people. What are my degrees of freedom? 91. I spoke to 1,001 people. What are my degrees of freedom? 1,000. I spoke to 98 people. What are my degrees of freedom? 97. And does everyone hear all we're doing is just doing the formula n minus 1? And that is for a 1 sample T. We can use that for a confidence interval or for a test. So you see the 2 things on there, and you see the n minus 1. Now, the second time we talked about degrees of freedom in our class, you'll see it has DF right there. Sorry, onliners, you might not be able to see this. Pull up the formula sheet too if you want to review it. We are on formula sheet right now, and maybe I'll try to do, my gosh, the video I see is very bad, but the audio is apparently good. I'm going to stop worrying about this. We're just going to continue on through. So, watch this only be like 20 people got, I know there's not 20 here, but there's enough with online. 20 people got a decent review. But hey, that'd work. It's good for you guys, right? So what we have right here is the degrees of freedom formula for the 2 sample T. And the degrees of freedom formula for a 2 sample T is a complicated formula which we will not have you do by hand. So do not worry about it. And the question came up yesterday. It was a great question. It was, well, how are you going to test us on that? That's about the extent by which we can test you. The extent which we can test you is the degrees of freedom formula is a complicated formula that we don't really do by hand. We've written multiple choice questions where it says for a 2 sample T, the degrees of freedom formula are n minus 1. A, it's n minus 1. B, it's n minus 2. C, it's rows minus 1 times columns minus 1. D, it's a complicated formula we won't do by hand. And the answer, as I've been stating multiple times, is D. And if you notice, I gave some trick answers there, and I also gave some answers which are other answers for other degrees of freedom. So don't be tricked by that. Degrees of freedom formula for an independent, 2 independent means is a complicated formula we will not do by hand. If you also notice, I said 2 independent means, which is the 4th condition, and when we order them, the 4th condition when testing 2 means. I won't do that yet. You knew I was going to yell. I was thinking of yelling it out, right? My class is ready to say what? What were you going to say, and what do you think I was going to say? Condition 1. They know it. Okay, let's continue on here. We have the last degrees of freedom formula. And this is one of my favorite ones because it's pretty easy to do. It's rows minus 1 times columns minus 1. And for this one, it would be questions like, we went to Walmart and Target. And actually, we can do 2 proportions here. Because we can go to Walmart or Target, and we can ask people if they bought milk, yes or no, right? Because both of those questions are what? Categorical, categorical. Does everyone hear that? And that's kind of why in the years past we took out the 2 proportion test, because we used to do the 2 proportion test when you had to do P1, P hat minus P hat 1 minus P hat 2. We no longer do that. We just do it with the chi-squared, which you can do. Because when you think about this, Walmart and Target is categorical, and buying milk yes and no is categorical. Now you should be able to tell me, take a moment, how many degrees of freedom does this test have? They got it like that, 1 degree of freedom. Because you would say to me, Brian, this is a what by what? 2 by 2. Brian, this is a 2 by 2. There are 2 answers to the first question, 2 answers to the second question. Brian, this is a 2 by 2. Now reduce it. That makes it a 1 by 1 when we do the degrees of freedom. And I'm literally doing that formula on the screen. Because when you do rows minus 1, well, 2 minus 1 is 1. When you do columns minus 1, 2 minus 1 is 1. So then we get 1 by 1. How about, let's try another one. We're going to do class at UT, and just think general class at UT, and let's do born in Tennessee. So take a moment and try to write this down and figure out the degrees of freedom. Now, is this the right chapter I'm in? I'm doing what class is someone in at UT, and were they born in Tennessee? Is this the right chapter, Chi-squared? Why, yes or no? Class at UT, like freshman, sophomore, junior, senior, and were you born in Tennessee? Am I in the right chapter?
Yes.
I am, because both those questions are categorical. Did everyone hear that? So we have a categorical. And Mohammed, he said 3 degrees of freedom. You are correct. Because you'd say, Brian, that is a what by what? Class at UT, how many levels? 4 by 2. Because we're freshman, sophomore, junior, senior. A 4 by 2, which means we have how many degrees of freedom? 3 times 1. Now, on the test, I got to say this because I get worried. Don't write there are 3 times 1 degrees of freedom. Solve it. What we're saying about when we say 3 times 1 is we're just saying the formula. Don't write the formula. I mean, write it when you're solving it if you want, but don't say there are 3 times 1 degrees of freedom. Technically, I guess they should accept that, but write 3 degrees of freedom. So let's try one more right here. Let's do what state you're born in the continental United States, and also what class you are at UT. Uh-oh. Bring out your calculator for this one. It's not that complicated. Ooh, it is a little worse than I thought. So what state you were born in at what state you were born in the US, and your class level at UT. See if you can solve that one. And let's review again. Does this meet our guideline for this chapter? It does, because state you're born in is a what question? Categorical question, and class level at UT is categorical. In this instance, you know you're doing chi-squared. So what do we have there? What are the degrees of freedom? Well, let's say it like I say it. You ready? Brian, that makes a what by what matrix? 50 by 4. Does everyone hear that? Because there are 50 states and there are 4 classes. That makes the degrees of freedom formula, drop them each by 1, 49 times 3, which equals 147, right? 147. Did everyone hear how we did that? We made it super complicated at the end just to see if we could graduate from doing it to an easy level to a harder level. So for those who just came in, wrong screen, we've went through all of the notation, and this is recorded, so you will be able to watch it, and hopefully in high def. Let's hope for that. So what do you guys want to do with our last 30 minutes? We could do some practice problems right now, and we will come back. We're going to go for 30 more minutes, then I'm going to go get some lunch, and I've got to do a talk. And then we're going to come back at noon, start broadcasting live. Hopefully the quality's good. Were you watching it online? Okay, I thought maybe like you might have come down here because the online, and we'll see. Is the quality still decent, my onliners? Who knows? 8 people watching now online. So what would you guys like to do because I'll let you guys choose. What do you want me to cover right now? You could say practice problems. You could say do a problem on the practice test. What would you guys like? A practice. So let's make up a practice problem, right? Let's make up a practice problem. So let's do this. And I'll probably post this document I'm doing right here. I'll post it onto, as long as I don't delete it or something crazy. I know they wanted a practice problem live online. So let's see. So let's make up a practice problem. I'm going to pick a random problem, and you have to figure out what you have to do with it. You ready? So let's do this. Okay. We went out and spoke to 200 random students. We asked them what they think they will score on test 3. The average for the class, it will be posted, yep. Thank you very much. All online are saying that. Oh no. The average for the group we talked to was, let's go optimistic, 85 with a standard deviation of, let's go 10. The distribution had a slight left skew to it. I knew I missed that at L. Create create a 95% confidence interval for what, see, I don't want to give it away. I can give it away if I say this. For what students really think they will score on the exam. So I'm trying not to give away with some keywords because I want you guys to try to think out the keywords. A lot of times we drop a lot of keywords on the test. If this was a test question, it'd be written a little bit differently, but I want us to kind of think what this question's getting at in the notation of this question. So there's some key things in here. Immediately when we see this question, we should start circling a few things. The first number I would circle is what? Sample size. Nice job. That's sample size right there. I literally circle these things on your test. If you see a number, circle it, and you should be like, what is that number right there? What does that number mean to me? That's the sample size. So then what do you see right here? I mean, I basically give it away. And just for those wondering, 200 will be n. 200 will be n. So what will 10 be? Standard deviation. Thank you online for the comments. I can see everything commented online. There is like a 20-second delay. So if you ask a question online, I will answer it. And thank you very much, onliners. So the standard deviation is there. What else do we have in this? I see one other thing. This will be S. This is S in notation for formulas. And then I see one other thing. Y bar. This is Y bar. Because this is the sample mean from the students we talk to. Does that make sense? That's the sample mean from the students we talk to. So I think we pretty much have everything. Let's give this a shot right here. And I'm going to cross our fingers. We're going to do some fun stuff here. I'm going to show my calculators again. And I think we have everything we need. So what we're going to do now is we're going to create a what with this? We're going to create a, I think, are you guys saying it? If you saw this on the test, you notice it wants you to make a confidence interval, right? That kind of narrows down the formulas to look at, right? So you really only have two formulas. I know I'm going to ask you guys for a wrong answer right here, and actually I don't think, well no, we have three formulas, but on our test we shouldn't have the confidence interval for this. Hopefully we didn't include that on our sheet, but that's for a proportion. That was on the last test, and I don't see Y bar in that, right? Also, we only have Y bar. We don't have Y bar 1, Y bar 2. So which one? We are doing a confidence interval for one mean. Does everyone see that? Confidence interval for one mean. So here is our formula right here. And I don't think I can copy paste that, but I might. I'm going to try something crazy here. I'm going to try to screenshot this. Let's see what happens. Oh. Ooh, what's it going to do? This is all like bad idea. Like I'm screenshotting, I'm streaming live, I'm watching the live stream also. Oh no, is it going to be a screenshot that killed us? All right, and then screenshot went to oblivion. Is it now on this desktop? Nope. All right. Well, let's do the formula ourselves. You guys ready? Oh no. Do you ever get the scrolly wheel when you're doing a Word document? That's bad news. Okay, so what do we need to do here? I'm going to write the formula out for us. We've got everything we need, and let's go through. Let's just grab our Y bar right here. It's going to be quicker if I grab it here. Copy this Y bar, and I think that's one of the few things we need. Y bar. Oh, really? No bar? Equation editor. Sorry, guys. The hardest thing to do is to accents, because I want you guys to be able to see the formula too as we do it. And then we need Y bar, and then remember, work this with me. Every confidence interval has with it a what? A, after the plus or minus means it is a margin of error. Everything after the plus or minus is a margin of error. That's a good note to make. Whenever we ask you for a margin of error, we might have it on the test, like find the margin of error. That's this part of every formula. Does that make sense? The margin of error is the plus or minus. Like when you hear in the news, the presidential approval rating is 42 plus or minus 3%. Where's the margin of error? It would be that plus or minus 3%. So we have here plus or minus. Now we are doing a t, and this has with it n minus 1 degrees of freedom. So I guess I got to go up here to a little subscript. Let's write the full formula real briefly and just review it. We've got time for a few more after this. So it's t with n minus 1 degrees of freedom, not n minus a. T with n minus 1 degrees of freedom. And then we go right here, and we do our last thing, little radical, and we do s over square root of n. So if you notice, I've set you up perfectly for this problem so that you can get every part of it. Now, once you have this right here, once you have your formula, you'll notice you already know the sample size. That's 200. You also know the standard deviation. The standard deviation is 10. You also know the sample mean. The sample mean is 85. I want to take away that bar. There we go. 85, we're good. Now the t with n minus 1 degrees of freedom, we might have you look at applet pictures or something like that to get. We can have you look at applet pictures, or sometimes we can just give it to you. But how many degrees of freedom does this t have? 199. And you should know that instantaneously, but I'm going to ask a more advanced question here. If you've never heard this, that's all right. A more advanced question that a lot of people don't know is the following. The t with enough degrees of freedom gets very close to the normal curve, z, yeah, normal curve. I was looking for a z-score when I said it in my head, but z-score is the normal curve, right? Now, you're not meant to know this. This is like more advanced, like high-level stuff, don't worry. But when I hear that the t gets kind of close to the z, I know that this t statistic is going to be very close to what? I'm making a 95% confidence roll, so the t statistic will be very close to 2, even closer to 1.96. Because remember, 68, 95, 99.7. A 95% confidence roll is very close to 2, more exactly as a z-score, 1.96. You're not meant to know this. What you are meant to be able to do is understand the applet pictures. So we need to go here, and let's go back. And here we are. We're going to show the secret pages, and I'm going to cost myself a lot of money and crash the Steps 1 page. So it's in a few of our videos. We've already shown where the secrets are at. If you go to this normal, or you go to the distribution tab, so you have to go to the distribution tab. Does everyone see where I'm going right here? I'm on the distribution tab, and then I'm going to type T. So after that, it'll auto-complete, and it'll bring you to my applet. Now these are applets that I had some help creating, but I kind of took the lead on after my friend kind of made the skeleton of it. He made the normal one, and then I made it a little bit better and made the t and the chi-squared, and I think I have an f. I don't know if I have an f distribution. Actually, no, I don't think I do. But here is my t distribution, which is basically meant to look like the David M. Lane. Problem was when we put this online, everyone used it, and I didn't realize what happens when you have a couple hundred students using the applet at the same time, and we got emails from students saying, I've been waiting about 10 minutes and nothing's happened on the applet. So if you go to this applet and it doesn't work, it's not my fault. It's just because everyone knows about it now and they're using it again. So you'll notice you do have the links under here under online resources, distributions, and this will bring you to a T applet that always works. I like mine though because it's more animated. It actually shows you the areas, but it might not work if everyone's using it. Now you'll notice with the degrees of freedom, we get a different T. Mr. T comes in and he says, "Appelez-vous," and smashes it down. You notice it's already a little bit slow. We probably got a bunch of people going there now, or it's just my internet. Do you see it rising back up? Do you see the T becoming more and more what? More and more normal. And watch as we go from 1 degree of freedom, not 81, 1 degree of freedom, heavy tails. And then when you go to like 11 degrees of freedom, more normal. 111 degrees of freedom, even more normal. It never actually becomes normal. It's never perfectly normal. It would need how many degrees of freedom to be perfectly normal? Infinite degrees of freedom. But really after a certain point, it's basically normal. And to show this, let's go to value from an area. And, oh, wait, we're going to round this to 2 digits. And you'll notice it's 1.96. And that probably, if we were to round R's to 2 digits, I shouldn't put in 200. Ooh, wait a minute. I think I made a mistake. Oh, no, I didn't. Do you notice the degrees of freedom? What are the degrees of freedom for my problem? N minus 1. I thought I put 200 for a second, but I didn't. Someone had caught that and said, Brian, you don't know what's going on. So if I am correct, this should be very, very close to, I'm guessing it's not going to be 1.96. I'm guessing if we round it to 2 digits, it'll be 1 0.97. And the answer is, it is 1.9. So you just guess the t. That's how I do it a lot of times where we're like, how do you guess the t? And it's like, well, it's got a lot of degrees of freedom. It's going to basically be the z. And we said it's going to kind of be 2 because it's a 95% confidence interval, but the t is a more exact calculation. If you guys remember the story, I'm going to go through it super quick in 30 seconds. William Gossett worked at Guinness Beer. He was drinking a bunch of beer and realizing he could make intervals, and then he keeps seeing that his intervals are wrong. So he made up the t statistic as a more exact calculation. So his t statistic takes into account smaller sample sizes, and when the sample size is smaller, the t statistic has in it more variation. So when you have smaller sample sizes, do you see how my interval's wider? I'd use a t of this, and the t is part of the what? The t is part of the margin of error. So if the t is larger, the what is larger? The margin of error is larger. Does that make sense? So the t is part of the margin of error, and the t gives your what, or the t is controlled by your what for your margin of error in a confidence interval? T controls the confidence level. So I could have changed my question very quickly to let's make a 99% confidence interval. If you notice this is a 95%, I'm going to make it more traditional looking, because you say, Brian, wait, that was the top 2.5% shaded. Well, the top 2.5 is the same as the middle 95. Because what would be over here if we have 95 shaded in the middle? What is in that right tail if 95 is in the middle? 95 inside, total outside, 5%. One of my hands, 2.5. So make sure you look at the graphic and understand what it's showing you. Does everyone see how this is a 95% confidence interval? Also, this right here, let's change it. What am I going to write? I'm doing the outside. I want to make a 95. What am I going to write? 5%. Is that a 95% confidence interval? Does everyone see how it's giving the same numbers? Is this, let me ask you guys this. Let's do a question here. What confidence interval is that? And I'm not looking at the screen. It's a what? Careful. It's only shading the lower tail, right? So remember when we make a confidence interval, we shade the middle percent, right? So then we'd have two tails with equal percentage on the outside. 96% confidence interval. Because think, if you had shading on both sides, do you see, remember that value, 2.07? Remember that 2.07? There's that 2.07 again. Because now you have the two tails. And if 4% is on the outside, what's on the inside? 96. And this is also, we're kind of bridging topics. I'm going to go back to our question and answer it before this section ends. But this kind of shows you that tests and confidence intervals do the same thing. Because a 96% confidence interval works mechanically the same as a two-tailed test with what alpha? 96% confidence works the same as a two-tailed test with, careful, 96% confidence works the same as a two-tailed test with 0.04 alpha. Does everyone see that? And do you see how it's the same number? Mechanically, a 96% confidence interval works the same as a two-tailed test. And just think, confidence interval is the area inside. A two-tailed test is the alpha on the outside. Does that make sense? So if you have 96% in the middle, what is in the tails on the outside? 4%. So just to review, one last quick mini question. What confidence interval is Brian building now with this right here? A what percent confidence interval could be built with that t statistic? 90%. Did everyone hear that? And if you want to check, you could just go here to between and make it the more traditional looking one and do it like that. Because remember, I just did 5% on that lower tail. But confidence intervals, if you're doing the tails, should have both tails shaded, right? Kind of good review questions. Well, going back to our main question, let's take that 95% confidence interval t statistic, because you know what? We're done. I mean, we did it. We got all the numbers. Now it's just solving it, and we're going to really reach a very good point. Good. Okay, 1.9, wait, wasn't it negative? It's going to plus or minus, right? So it doesn't matter. So the plus or minus is going to do plus or minus that amount, and that's why if you do the 95, you get the negative and positive version of it. So if you notice here, I'm going to try to solve this in my head. So for those doing it at home, go ahead and try to do it. Don't tell me the answer yet. Part of the fun is guessing this. Gotta have some fun, right? You're like, math? Fun? I'm like, yes, math is always fun. So 14, so that's about I think it's about 1.4. Okay, I think I got my guess in my head. So let's do this real quick here. Let's see. What you guys got, I am taking a guess right now. We'll have someone in class say the answer. I want you at home to do this problem on your own. I want you to solve it. I want you to punch it into your calculator and see the result you get. Now, this is me guessing. I might not be getting it right here. I could be very off, but I hope I'm close. Punch it in on your calculator and see what answer you get. If it's very different than this, then I am wrong. I do not know the answer yet. I am doing the math in my head.
So it's close, very close.
Ah. If I had to change this decimal place, if I had to change this, I would change this to a 5. No, it's a 7.
No, it's the second, it's the upper bound. 86 point.
Oh, wait, oh, no. Oh, I know what it is. Why did I do that? Oh, no. I'm sorry. No, that's it?
Yeah.
Is that it rounded to one decimal?
Yep.
Okay, then I gotta guess the next decimal. Are you ready? All right, don't tell me.
Nope.
What is it?
It's 3.94.
394, okay. So if that's, it's 86.394?
Yeah.
Okay, so rounding it. 39, I'm just gonna put 39 there, and that would make this one, don't tell me.
How many
My brain
decimals?
broke. That would make this one right here that, right?
Yes.
All right. On the test, I think it says on the cover sheet how many decimals to round to. Do not quote me on this. It either probably says 2, 3, or 4. I can't remember. I've seen it. But it does say on the cover sheet how many decimals to round to. Are you guys in my section last time when I was like, round to 2 digits? And I was like, wait, round to 4. Because like a student like raises his hand and he's like, Brian, on the cover sheet it says round to this many. I was like, yeah, do that. We change it so much because different questions require different rounding. And sometimes I have a number in my head that we've used on previous tests. Look at the cover sheet. Whatever the cover sheet says, do what the cover sheet says. Don't be like, Brian said on the review round to this. Don't do that. Do what the cover sheet says. Okay, I want to see. Now, if you notice, as they were telling me the answer to this, I changed my answer. Because what did I notice? Can you tell me, and it's weird, what is the margin of error for my interval, just looking at this right here? When you say it again? 1.39. So, and I realized I made that mistake when I typed the 6. I was like, wait a minute, I went 1.4 down, I should go 1.4 up, and that's rounding it to one decimal. I just was typing in, didn't realize I didn't do the margin of error the same. The interval should be symmetric. If you go up this much, you should go down this much. And just think about this mechanically. If you went out and spoke to students, and the average test score that they told you for their best guess of their test score was an 85, then what should be at the center of your interval? 85. I mean, like, the average they told you was 85, so your best guess of what students think they'll make on the test is an 85. So with this right here, and we might have broken one condition, we'll check that out in a moment, 85 would be your best guess, and that is at the center of your interval. So the sample mean is your best guess, it's at the center of the interval. The margin of error of this interval is 1.39. We can see that because it goes up 1.39 and it goes down 1.39. And with our last little bit of time, I'm going to do a very important review right here. So we're going to do this, and you guys might know what I'm doing right here. I'm not going to do conditions. We'll probably come back and do conditions to just review and go through each condition for each test. Then we'll do more practice questions on different types of questions you could get. So I want to make sure we can interpret this interval. Here is Brian's way to interpret every confidence interval. I am blank % confident that the true, and we're going to put blank right here, is contained in the interval blank to blank. I am blank % confident that the true blank is contained in the interval blank to blank. So let's talk about the hardest part for this for students. The hardest part for students on this is the second part. The first part, I am blank % confident. What do you guys think? I am 95% confident. So just state your confidence level. I am this percent confident. You'll notice on my Pearson it might say, we are 95% confident, or one can be 95% confident. Just say it the same way every time. I ask my students all the time when you see that my Pearson question, don't even read their answers. Say it yourself first. I am 95% confident. The true difference between the hot dog weights of meat hot dogs and beef hot dogs is contained in the interval blank to blank, where meat hot dogs have a higher weight by this or maybe a lower weight by this. Like, try to do it yourself without looking at their answers, because that's going to prepare you for the test. So if you're reviewing my Pearson assignments this weekend and it shows you, here's the interpretations. Don't look at their answers. Write it yourself down first, which is really good practice for the test. Looking at it and just kind of contemplating it, that's probably not the way we're going to ask it on the test. We're probably going to have you write it. So when you do a My Pearson question, don't worry about, yes, I got a My Pearson question correct. Wouldn't it be great if every My Pearson question was the exact way we ask it on the test? I'm sorry, it's not. But when you do a question where it asks you to interpret an interval, write your interpretation down. Then look at the interpretations it gives you and see which one is closest to yours. And do it the way I'm doing it here, because this is the way we try to get, at least I try to make sure you get all the points. There are other ways, there's other ways to say it, but I've got a standardized way, and usually I have some hand in writing the key. So right here, I am 95% confident that the true, here's where we pause. What were we measuring? You have to ask yourself here on question 2 on this blank, what were we measuring? Well, mean what? We need context. And whenever it says interpret your interval in context, the average, the true average students think they will make on test 3. And that's a lot to say. A lot of people usually don't give enough words. They usually say true mean, that's all right. You might lose a point, like maybe it's a 4-point question. You might lose a point for just saying true mean, but we want the true mean score that students think they will make on test 3. That's a lot to say, and usually people don't give enough information. I am 95% confident the true mean score students think they will make on test 3 is contained in the interval 83.61 to 86.39. And that's, once you know the second part, it's not so bad. The first part, you're just stating your confidence. The third part, you're just stating your interval. The second part, you're stating what you're talking about. Break it down into parts. It's easier to remember when you think about, like, I have to remember these 3 things. Like, you remember, oh, I have to remember a whole interpretation. Have you guys ever memorized the Gettysburg Address? Or why do they have us memorize things like that, right? Like, 7 years ago, upon this continent was, is that right? It's close enough, right? It's close enough. I don't know why we have to memorize these things growing up, but when it comes down to it, there's a correct way to say this. And a lot of times I'll see people on the test interpret their interval like, my interval is good. It contains the mean. Wait, what? No! There's other ways to say this. If I wasn't in Stat 1, I might say, well, when we went out to speak to students on how they felt about how they do on test 3, it looks like the truth for how they feel, the average for what they would really feel, is probably somewhere between 83.61 to 86.39, and we have a 95% confidence that the truth is contained in that interval. I said nothing like I'm saying right there, right? But the problem I found in the years of teaching this class, if I say to you guys, there's many ways to interpret this, it just goes haywire. But if I set it up in a way to memorize it, that you can say it pretty much, you can say it differently. There's other ways. You can change some words. You can say we are, I am. You could say what I said and be like you would at a board meeting, saying it more technically, like when you're actually talking to someone, like with the sample we spoke to, we did see this, and we're about 95% confident that the truth for what students actually think is contained in the interval, and you basically told them what we're trying to consider here is what students think they will score on test 3 on average. So with that, you could do that, but this is Brian's method right here to not get it wrong. There we go. Wow, they are lagging behind by a lot of time, it looks like. Chelsea, I do not know the answer to that. So let's do a little wrap up here with your guys' questions, because I'll be heading out in about 5 minutes. Then we will return at noon, and I'm going to see how this broadcasted live. I'm going to cross my fingers. This has looked very, very slow and choppy online. We got 5 people watching. Let's just check ourselves with what we wrote with this test question. I think there's one violation here. Condition 1, do we pass the random condition?
Yes.
We do, because the question states it's random. We'll be very clear on the test. Condition 2, less than 10%. Now, we don't usually try to write trick questions like this. I should have said we went down and spoke to all UT students, but all UT students don't take Stat Tool 1. About how many students take Stat Tool 1? A little more than 1,000. So let's pretend it is 1,000. Do we meet the less than 10% condition here with 1,000? We don't. So we violate the 10. I wouldn't write a test question like this. This is not a perfect test question. It's just an example, and we're just doing conditions very briefly just to check to see if we know them. Condition 1, random. Make sure it's randomly sampled. Condition 2, less than 10%, and we violate that because 200 students is more than 10% of all Stat Tool 1 students because there's 1,000. You could then show the formula. 200 divided by 1,000 is what percent? 200 divided by 1,000 is 20%, 0.2, 20%. Does that make sense? So you've violated the 10% condition. Now, condition 3, I did give away condition 3 in this one. Condition 3, we have to pause. And what kind of data are we dealing with? Quantitative data. Condition 3, quantitative data, means we must check the what condition? Nearly normal. Nearly normal. The normal enough or nearly normal, called nearly normal. And I gave it away here because I said we sampled how many? 200, and the distribution is only slightly skewed. Do you guys see in the question where it says the distribution had a slight left skew to it? So when it's slightly skewed, and I'll go by what it says in the notes for this last chapter, I think it says 30 to 40 if it's slightly skewed, or I think 30 to 40 if it's